Hey, this is Steven, and we're here going to look at a video talking about a 3D printer and his design and how he designed this printer. And I think this is a pretty cool video. And I do printers because they're kind of simple. They're simple yet complex machines. Generally, they're small in size, but part count is pretty high and complexity is pretty high. You have software and hardware mixing, as well as electrical and hardware, right? So I like to talk about printers because um, that's because of those criteria. So also, this is a pretty rare video just in general because this is actually a commercial product that you're going to be seeing. This is version 1 of this printer, and now he's got to version 3.2, and it's being sold as a kit, and I think it's been being sold for like a year or so now, and he'll go through kind of his design process here. Let's go ahead and get started.
Printer or take your 3D printer to work or school. For anyone who has tried that, you'll know that it is a massive pain to do so.
One thing to remember during this is I think I talked about it in my school group. I have a school.com group for hardware development. Link is in the description. And I was talking about kind of what I'm doing. So I'm focusing on getting 2 certifications to learning now and developing my hardware development procedure. And that is the NCOSI System Engineering Associate, as well as the PMP, which is Project Management Professional from PMI Institute, focusing mainly first on the NCOSI and then maybe PMP middle of next year. So hopefully NCOSI start of next year. Anyways, so in those and also other places that I'm learning is that one of the main things is the DOW definition of winning, as well as HVP, high value problem. So basically, what defines a winning product in the market that you're trying to target, and what is the high value problem that you are trying to solve? So, um, and if you solve the high value problem, it should be difficult to solve. It should give you and your customer a competitive advantage and just be great in general. Now, um, if if it succeeds, then it should be no problem to get a customer to pay for it because it provides so much value. Now, if it doesn't sell, it means that you've missed something. Either the high value problem is not a high value problem, or your solution is not a great solution to that high value problem. And that could be many variables: size, cost, weight, footprint, power requirements, cost of ownership, all these things, right? So let's go ahead and continue, but keep in mind the high value product and the definition of winning are the 2 main important criteria.
Well, what if your 3D printer fits inside a filament spool box so you can easily take it anywhere you go? Introduce
So if you saw in that box, that was the entire printer fitting into a spool box. So that's about a 6 inch by 6 inch, because it's circle, 6 inch by 6 inch box by like 3.5 inches thick or so, or 3 inches thick. So that has never been done before. And so basically, he's talking about portability. So the question mainly is with your customer, is portability a high value problem? I would say probably it may be to very few, but what's the actual size of that market? So how many customers are actually looking for it? The interesting thing about that I found with this, thinking about it, and I've been watching this project for a couple of years. He started about 2 years ago designing this, and it kind of started maybe 6 months ago to start selling kits. But one of the things is this would be great for, hey, I can get it in a small box and I could ship it all over the world for basically nothing because it takes up so little volume, right? But instead, the funny enough thing is that they're selling it as a kit that you have to build, and supposedly the kit assembly is quite challenging, according to a video I watched a couple days back to get to kind of look at this again. So just keep that in mind.
using the Positron, an upside down compact 3D printer capable of accelerating up to 8,000 millimeters squared per second while maintaining beautiful quality. The printer can be easily set up and packed up within 90 seconds, so it can be easily taken anywhere you go. It manages all the functions above while maintaining a gantry that is more rigid than most 3D printers on the market. You might be thinking, a foldable 3D printer the size of the filament box must have abysmal print volume, right? Well, the Positron actually has a massive build volume compared to its footprint. And compared to two other printers with a similar footprint, the Positron actually has 8 times the build volume of the Fulcrum Minibot, and double that of the Voron V0. In fact, Positron's build volume is
V0,
large enough to print almost any 3D print I have ever designed. How is the printer able to achieve these specs, and why does it print upside down? These questions will be answered after this quick sponsor message.
Remember, this is V1.
This video is sponsored by
V3.1.
This video is the first one in a multi-part series, of which I will be going over a step-by-step process of making this printer.
Precision,
For this first video, I will be showing the capabilities of this printer, as well as showing some beautiful prints that this printer has produced. As for always, all the design files and the resources are linked down in the description. And by the way, if you like what I do, please consider subscribing to my channel. And please stick around for an exciting announcement at the end of the video. So to answer the question in the title, why is this printer upside down? Well, the main reason is maximum stability at minimum weight, which is essential in a portable 3D printer.
Keeps the gravity down low.
3D printer heads are not light, and they are usually being swung around by the motor at high speeds and accelerations. As a result, this can cause the whole machine to shake. So 3D printer designers add a heavy and thick frame to make the printer more rigid. But by flipping the entire printer upside down, the heavy moving mass is now close to the ground, no matter how tall the print is. This way, the center of gravity is always near the base of the printer. Thus, only a sturdy base is needed for the gantry to be stable. In this case, a 6mm aluminum plate. Another benefit of this upside down structure is that now the X and Y axes are both on the same plane. Most foldable 3D printer designs fold down the X and Z axis, which can make the printer realignment quite tricky. However, in the case with the Positron, the X or Y axes are never folded, meaning that the gantry will always remain square and perpendicular. Speaking of the gantry, this printer uses a unique cable-driven inverted H-bot design, which is inspired by the same belt-driven design by Lobo CNC. Link in the description. This particular type of gantry moves the same way that a core XY mechanism does.
So I mean, pretty cool, right? So he uses these, he'll talk about it. Basically, these are belts. These are like timing belts that have this grit, this kind of grip thread on it, but it doesn't, you have to worry about the belt twisting when it's making these turns. So otherwise, that's why he's not using belts, because the belts will twist, and when they twist, you could have issues of them coming out, you know, the tolerancing being difficult to keep because of that turning. So in this case, there's no twisting of belts because it's just a straight cable, and but yet it has enough grip so that you don't have to worry about slipping. So here he's talking about H-bot, which is kind of the leading design for 3D prints currently. H-bot, Core XY, basically same thing.
Because it uses these synchromesh cables, belt twisting is no longer an issue. The main reason why the 3D printer can be so compact is because of the way that the gantry is mounted on the base. If I mount the gantry lengthwise along the square base like this, the longest the gantry can theoretically be is only 200 millimeters. However, if the gantry is mounted edge to edge, the maximum length is now increased to around 280 millimeters. This simple change can actually more than double the print volume. Since the Positron prints upside down, if it had an opaque build plate, it will be quite difficult to see the print. So I spent a lot of time designing a transparent
So that
build.
was another thing to kind of add on top of his high value problem. So he's like, okay, I can get a regular box printer to fit in a box. Oh, also I discovered that by putting the base down, I can actually and go into a square box. Most boxes are square that you ship it in. And I can actually rotate 45 degrees and have it be a diamond, or basically a 45-degree rotated square, and get, double the print volume out of it for the same size.
Plate. And the final result is a piece of borosilicate glass covered with copper heating elements. These elements are actually quite easy to find, as they are the same as a car's windshield. I believe this is the only FDM 3D printer where you can actually look through the build plate at the bottom of your first layer, which creates quite a mesmerizing experience, as well as making the first layer adhesion issues very easy to spot. Because of all the unusual changes done to this machine, there is not enough room for a standard hot end. Instead, now the hot end takes a 90-degree turn, where the filament comes in from the side and goes up to the nozzle. It took me over 6 revisions to get the hot end performing well, and because of the increased melt zone, this special hot end can push more plastic than the E3D V6. And
basically, he's talking about here, he has a longer melt zone because it has to take that 90-degree angle. So basically, the melt zone's double the length that it used to be.
Extrusion issues so far. Everything in this printer has been designed to minimize space. The extruder and the Z-axis mechanism are both driven by worm gears. The precision machined Z-axis connect block.
So here's kind of how, so he's doing worm gear here, so you can see that he's attaching here with a coupler. And he has this exact precision block here that will tie in the vertical rods into the printer so that you can take it apart. It doesn't actually fold. You unbolt it and put it forward, and then you rebolt it again.
Matches up with the grooves created by the linear rails on the Z-axis tower. This makes it so that every time the Z-axis will be always matched up perfectly straight and perpendicular to the printer body. In terms of features, Positron has basically all of what you expect from a premium 3D printer. The firmware uses the Clipper firmware, which means that it has unique features such as smooth pressure advance, resonance cancellation, and being able to start a print from any device near the printer. Positron also has all the other standard features, such as automatic mesh bed leveling, OLED display, dual drive on the extruder, and also filament runout sensor. And don't forget the RGB LED to go with all of it. With all of the features explained, let's see how this printer performs. Because this printer prints upside down, one of the most obvious questions is that does the print fall off the build plate? The answer is no. The prints actually stick very well to the sheet of glass. And upon cooling, the prints also automatically release themselves. The only time where I had prints falling off the bed was due to warping and the nozzle knocking them off.
PTG or
in this
PLA,
case, the print is still going to fail, even if the printer is printing right side up. Another big question is bridging. Can this printer print long bridges? And the answer is yes, and surprisingly well actually. In fact, I think the nozzle actually pushes up against the bridge slightly during each pass. So even a 50mm bridge is no problem for this printer. When I designed this printer, I thought the supports are gonna print quite horribly, since I thought they rely on gravity to work correctly. So I try to print the most intensive support test I can think of, which is the impossible cube. But the results actually surprised me, as the printed supports are just as easy to remove compared to my Prusa i3 MK3. And the underside of the print does look decent also.
So here's him kind of testing all the missions in a POSI is called a mission statement. So mission statement: how does supports go compared to the competitor? Okay, they work fine. How do the parts stick compared to the competitor? Okay, prints fine. How do the overhangs, bridgings, mission compare to the competitor? Oh, it might actually be better. Okay, so those are the different missions, and the requirements are beat the competitor. I have the competitor. Okay, let's beat it. So, and then you go through and you do some of these analytical testing, like that bridge, and then obviously a lot of this has to do with how does it look? Does it look better? Yes. Okay, then this is a win here. So basically, he's checking all of his system requirements and all the missions in different environments and different um, basically different requirements for each of these missions of things that a standard user would put this printer through and make sure that it will compete against any other printer on the market.
To get an apples to apples comparison, I printed two benches, one using my fully tuned Prusa i3 MK3 and the other one using the Positron. And they actually turned out nearly identical. This means that printing upside down nearly
Now there are some differences here. I mean, some he's got some sort of extrusion issue here, and then the hole here versus this one, and some overhang issues here. So I mean, these aren't the same.
identical. This means that printing upside down has practically no difference compared to printing right side up. To test the retraction and the mechanical accuracy, I printed.
So this is another thing that was brought up in the video, was this kind of mess on the nozzle. Because it's printing upside down, the filaments just kind of droop onto the
The
nozzle
retraction
and
and the
glob up.
mechanical accuracy, I printed this small piece of chainmail, which worked without any problems, and also this iris by Lobo CNC, which also worked beautifully without any problems. I used Kira to slice all my parts. However, the clip
So then
performer
here's
supports
another, like, okay, how do you get it to print correctly? Now, of course, here you just set your Z opposite of what it needs to be. So, Z, it thinks that the Z is at 0, but in this case, it's not. So I don't think...
G-code from almost all standard slicers. The standard print speed is 100 millimeters per second. This speed is enough to print a benchy in less than 30 minutes.
So instead of going down, it goes up. Commercial. So this is pretty cool. This is basically his kind of, I don't know what program this is, but this is kind of how he um, tracks all the things that he did. So in here, I can tell by the joints here, this is Fusion 360. So he just takes some Fusion 360 snapshots. So you can see that he started out with a bigger prototype, version A, version B. You can see he's got vertical motors here. Then he goes to horizontal motors. He's got a bigger Z gantry here. Goes to a smaller Z gantry. Z gantry on opposite sides. Now Z gantry is only on one side. So he went kind of back. Interesting enough, he went kind of back and forth. Version A, tower on one side. Version B, tower on both sides. Version C, tower on one side. Version D, tower on both sides. And then you can see, well, this is the gantry that's moving.
Printer took me over 6.
And then now he's getting closer, so he's got a vertical motor here, horizontal. I think this vertical motor might be for the Z. He doesn't even have a Z here. And then here he's got a Z sort of on one side, a Z on both sides using pulleys. He changed to using, I think he's using worm gear. He said worm gear earlier. And then, funny enough, he kind of gave up on this version, kind of went back to these two sides.
Month to design.
And then finally came up to, hey, if I have one sturdy 2 rails, put 2 rails on it, and then have these arms that come off and hold it at 3 positions, leave the other side overhanging. And this guy bolts in, and then get rid of all vertical motors. All the motors are horizontal, and then put the screen on the front.
And build. and I learned a lot of things along the way. I
And so here's all his other testing. So another thing also that tends to not happen is you want to evaluate your technology kind of like was this not the feasibility but like the maturity. So how mature is this technology? Has somebody done this before? Transparent bed with this, obviously it's done in cars, so you have somewhat of a think, okay, this technology is somewhat mature, but no one's ever done it on a 3D printer. Okay, I can get value by converting it, and it should work because we use it somewhere else, but we haven't used it here. And then, okay, let's test it. So now, what's cool about this is he's testing each technology in each component or each subsystem. So extruder, hot end, these ones, all the different all the different subsystems, and then validating. So you can see here's data. Okay, here is the uniformity. Can I get to this one? Where's the amperage? How does all that look? So here he's taking images of the uniformity. Okay, what? I have a 90-degree hot end. How fast can I feed it? Is there slipping? What type of cooling side do I need to have? Or here, okay, how do I design it? Different design iterations. How do I clear jams? All these things, right? So this is pretty cool. He's testing, because generally how you want to do it in system engineering is you want to test each subsystem separately and then work on the integration. They call it integration, which is putting all the subsystems of the system together and getting them to work. And the difference between each subsystem to the system are interfaces. So how do you interface each subsystem to each other? And are you going to use a standard, or are you going to create your own standard, right?
will share all of them with you in the upcoming build series. I will also
And then here you can kind of see his flow of his sketching,
continue to
which he's a
improve this
great
printer,
artist.
and if there are enough demand,
And so here he's kind of figuring out, okay, how do I hold on to it? And okay, I'm gonna have this diagonal bed, but then a regular square bed. Is that okay?
I will start to plan for a commercial version of
And then looking at, okay, I need to figure out how to do the cables with this. I'm going to have cables that are rotating. How do I do that? Okay, synchro mesh cables. And then he's seen this image, is he's seen it done before on another printer. This technology is somewhat mature, but it has never been done. Well, obviously this is that application, but it's never seen large commercial application in this particular application. So maybe also it's used in a whole bunch of other systems, but it's never been used in 3D printing. So
this printer. I am going to post the entire build series on this printer very soon. And all the design files and the BOM will be free, and relevant links are in the description.
Also,
finally, before I
so
leave you with
everything.
a montage of the printer, I have an exciting announcement to make. Sorry for the long wait, but now my power bank project is finally on the printer or the campaign. Please post them in the comments below. And now, for the montage.
So now the next question is, how many marathons has he done with this? And any sort of other design system famicas, or any sort of other safety issues? Because there's a safety issue. You have this guy open and you're touching the back of this glass, going to burn the heck out of yourself. So how you handle that with safety. Also, no enclosure, and these parts are kind of exposed to moving parts, pinch hazards, get the cable stuck, your finger goes to pulley, these things. So a lot of things here that are not covered with any safety covers or anything like that. So can you do a safety cover, or kind of like how a 3D printer has, or like a CNC machine has the kind of the gantry covers, sheet metal covers that telescope in and out past each other? Is that something that you can do here, or even cloth to prevent stuff from getting stuck? Because also his new version, they had issues of having a kind of an umbilical cord, and the umbilical cord getting stuck on the pulleys as it moves to the leftmost extreme. It'll get stuck on this guy. Also, something here looks weird. And also, has he tested the repeatability of the z-axis? Taking the z-axis off, putting it back, what's the positional repeatability? Any specialty tools needed for this? What filaments can it do? Can it do more rigid stuff? Right? Can it do flexibles through that 90 degree, or the flexibles don't work? Some of these Also, how long do these last? How long do these last, and do they slip? What's your maximum speed? Do you give, okay, obviously you gave a recommended speed, so most people will stay within that. But do these guys pulleys start wearing out? What happens if they start to kind of come out of round, or what if they aren't round? How does that work? You see here also he's got live wires to the face of this guy. So if you grab onto this plate of glass here, if you grab onto the edges, you're gonna get a nice shock. If it's unplugged or something, then you might have a lower resistance from one side to another. So you have also exposed things here. This should be coated so that it won't allow you to touch it. So his newer version, he has it doped. So the glass is doped so that it's actually, the resistance is built into the doping of the glass. And so the electricity actually travels through the glass instead of through these contacts here, which is pretty cool. So that may be why he's doing a kit, is to try to limit his liability a little bit, because there's some design and safety Famika issues here of different things that you can have happen to you. Because most of the time on a 3D printer, for the most part, the bottom is covered. Obviously, the top you can't cover, is printed there. So I guess you can think about it. If this thing had something over the back of the bed, that would make it super safe, because the chance of you touching the underside is way lower. The chances of that occurrence from the safety Famika is way lower versus on most printers where you can easily touch the top. That's the Voron square. It's kind of a turbo impeller, basically. All right, so final thoughts here in a minute or so. So one, great design here. Now the main things are, he always kind of wanted this to be a open source project, so safety and marathons and things like that have not been taken into account, because he's going to assume zero liability, shipping just components, and maybe not even a power supply. You have to get your own power supply or whatever. So, and that's where the kit comes in, because again, he can just say, hey, it wasn't me, it was you that put the kit together. So maybe you made a mistake that led to this safety incident. So, but overall, you saw his kind of design. I like that page where he shows all of the different versions that he's gone through. So he mentioned that it was 6 months, and this was 2 years ago. So it's been 2.5 years now developing this product. Obviously, it has some design features that make it less safe than some printers. So some of those would need to be addressed, but overall, as far as a machine that just works without that, it has got a lot of upsides. Okay, so that's it for this video. So I wanted to show you guys a pretty cool video I watched, so you can learn from it and check it out. So also past that, so he's got a website here. This is the Positron 3D. So it talks about the LDO kits, and then also probably the GitHub or Wiki where you can get all the documents. And then here's, for example, Wes 3D, which is one of his where he has an affiliate link. I don't know why he needs I guess affiliate link for his own design, but whatever. Um, so this is kind of the kit. And again, I think that this is kind of missing the whole. Oh, it looks like he went to one. Yeah, he went with just a wider z-axis, so now it's got a smaller z-axis. And then he has some sort of Bowden. Oh yeah, he switched to a Bowden system. That's right. So he switched to a Bowden system now. I saw that in another video. And kind of he's increased design here, gone from plastic to metal. And then it looks like he went to belts. So now he's switched to belts and avoided any sort of belt twisting. And here's kind of the shipping Positron kit for in this box, and then you can see kind of the full packaged system all inside of this filament box. Anyways, so I think it kind of, and then he went from that LCD setup to a touchscreen. So I think that it is a. So here's the official launch partner LDO systems. Anyways, and then you need also the printed parts, unless you're gonna print your own parts. And here's under $100 for printed parts. Anyways, I think again this misses the big high value problem that could have been solved, which is to have it shipped directly to you in this state, already tested and ready to go. I mean, it would ship pretty easily because it's designed to ship in a very small box, and all the weight is in that small box, and then you can just stiffen the heck out of it. But it's built to kind of withstand a lot of abuse, except for that glass plate probably, but they're using Persilica glass now, pretty strong. So that might be a miss there, and to ship it as a kit. But anyways, a pretty cool project, a lot of problems solved. He went to solve one problem, but was able to solve various other problems and do a lot of technologies that are in its infancy in 3D printing, but are used for decades in other industries. So basically took some highly mature technologies from other industries and brought it into an industry where it's never been used before. So that's another thing that I like about this project. Very, very cool. Anyways, that's it. Any questions, ask me in the comments. Check out my school group, links in the description. And I'll see you guys in the next one. Later.